Hello, my name is Dylan, and today I'm going to be talking about the quantum dot laser. This is the outline of everything we're going to be covering, so let's get right into it. So a little bit of history first. The quantum dot was first discovered by Alexei Ekimov and Alexander Efros in 1981. Since then, it's been used in biological analysis, displays, photovoltaics, and more. Quantum dot lasers, though, are novel. In 1975, the first quantum well lasers were created. In 1982, the first quantum dot laser was proposed by Arakawa and Sakaki. In 1994, the first quantum dot laser was finally made by a conjunction between the University of Tokyo and Fujitsu Labs. So before diving into the quantum dot laser itself, let's talk about the laser in general first. So there are three components of lasers. There's the pump, the medium, and the cavity. The pump is in charge of pumping energy into the medium in the form of electrons or photons. Now the medium is in charge of producing stimulated emission of light to ensure coherence of a beam passing through it. The cavity actually produces the bouncing of the light back and forth within, so that one side is reflective 100% of the time, and the other side is only reflective some of the time. This allows for the gain to happen within it, and light to come out of one of the sides. Now there's a very useful feature of diode lasers that is called double confinement. Double confinement basically says that we want electronic confinement, so we want the electrons and holes to recombine only at a very specific area, the medium, and not anywhere else. Now the optical confinement means that we want the light, the beam, to pass through this medium and not spread anywhere else. So we can actually make a waveguide. Now the quantum dot lasers can most of the time be diode lasers, where the pump is just current. So before we begin with quantum dot lasers, let's talk about quantum dots themselves. They confine carriers in 3 dimensions and are therefore zero-dimensional structures. Now, the quantum dot effective band gap actually depends on 3 factors: the material band gap, the quantum confinement, and the exciton binding energy. Now, all of these 3 terms add up to usually be a higher effective band gap for a quantum dot than its material band gap. Now, radiative recombination usually occurs on a very narrow quantum well when happening in a quantum dot. And you can see this on the picture on the right, where the recombination only happens in this very small area. The fabrication of quantum dots depends on its material. And different materials, as we saw, yield different band gaps. So I'm going to look at 2 different materials, and they are indium gallium arsenide within a gallium arsenide matrix and cadmium sulfide and cadmium selenide quantum dots with zinc sulfide and zinc selenide shells. Now these, again, yield different band gaps and therefore different wavelengths. So the alloy concentrations of, for example, indium gallium arsenide yield different band gaps. So the more indium there is, for example, the less the band gap will be. Now the shell on the quantum dots, especially cadmium sulfide and cadmium selenide, can lead to better passivation of the quantum dot surface, as we've learned in class. So having a shell on top actually yields to better absorption, as we can see on the right here. The problem is, in quantum dot lasers, we actually care a lot about the line width of the emission peak. And this also gets broadened because of the more elements that there are. So we'll start with indium gallium arsenide. Indium gallium arsenide quantum dots use MPE for deposition. Now we can see on the graph on the right that indium gallium arsenide would sit between gallium arsenide and indium arsenide, somewhere in the middle. Now because indium gallium arsenide and gallium arsenide are not lattice matched, it means that the Stransky-Krasnov method can be employed. Now this allows for little islands, and these are pyramidal islands, be produced on top of the gallium arsenide. Now these indium gallium arsenide islands are quantum dots. These islands range between 20 nanometers in diameter down to 10. MOCVD can be used for the non-quantum dot layers such as gallium arsenide and aluminum gallium arsenide. So several layers of quantum dots actually can be used on top of each other to produce more gain in a lattice. The indium gallium arsenide microstructure is very similar to that of a normal diode laser. Now this incorporates optical and electronic confinement within the microstructure. So firstly, optical confinement happens within the gallium arsenide and indium gallium arsenide layers. This happens because the gallium arsenide and the indium gallium arsenide have a higher refractive index than aluminum gallium arsenide. So a waveguide is actually created. Now for electronic confinement, a similar approach is taken. The aluminum gallium arsenide is actually of higher band gap than the gallium arsenide and indium gallium arsenide. And further, this recombination only happens within the indium gallium arsenide quantum dots, these pyramids, because it has an even lower band gap than the gallium arsenide surrounding it. Now the cavity is made with the cleaving of the edges to ensure the most smooth facets possible. And this cleaving actually happens right at the distance for the expected mode to happen, usually the 0th mode of light. After this, the depositions of metal or dichroic films can be placed to actually allow for light to bounce within the medium, making a cavity. Cadmium sulfide and cadmium selenide quantum dots are actually colloidal quantum dots. That means they're suspended somewhere. And they are usually accompanied by zinc sulfide or zinc selenide shells. They're usually synthesized with the following: MPA for the ligands, and you can see on the bottom left here that the ligands allow for the colloidal nature of these quantum dots and avoid agglomeration of the quantum dots themselves. Agglomeration is not wanted because it stops the uniformity of the quantum dots, as well as joining quantum dots can actually alter the band gap properties of the quantum dot. Now the synthesis actually is done with cadmium source, zinc source, sulfur source, and a selenium source in order to have all the building pieces to actually create these quantum dots. Now an interesting thing is this picture on the right here. We can see the different potentials and band gaps of the zinc sulfide selenium, as well as just the core itself. The microstructure of the cadmium sulfide and cadmium selenide quantum dot laser has multiple different approaches, but I looked at the inverted LED structure, which I found in a paper and I found to be very interesting. So this structure might look similar to the OLEDs that we learned about in class, but they're in the wrong order, some of the layers. Now, the HTL, the whole transport layer, is made of TCTA. The colloidal quantum dots are made of cadmium sulfide and cadmium selenide cores and zinc sulfide shells. And the electron transport layer is made of zinc oxide. The cathode is actually a low index ITO material. The low index ITO allows for more of the optical confinement to happen within the quantum dot array, which is where the gain actually happens. Now, this laser is a DFB laser, a distributed feedback laser. This means that instead of the light going through the quantum dot array, it goes still through it, but in a perpendicular direction. The light actually bounces this way, which is very interesting because where are the reflections? Where's the cavity coming from? Well, on one side, it's actually metal, so the light actually bounces off the metal and reflects off. And then the ITO is supposed to be transparent, but it actually has a DFB, grating type fabrication, which is actually fabricated with electron beam lithography, which makes the light actually reflect back and forth until it actually makes it out, because this is not 100% reflective. So it is also interesting to note that the actual optical confinement happens within the quantum dot layer because of its higher refractive index. So in more general terms, the quantum dot device performance is quite good, with output levels actually reaching the quantum well laser output levels at several watts of power possible. The bit rates are quite good at over 25 gigabits per second, and the quantum dot lasers actually have several advantages. One being better control over wavelength, because the wavelength can actually be set by the size of the quantum dots. Specific materials don't need to be developed for a specific wavelength. Now, the lower temperature dependence is very useful and is due to the lasing transitions being much more discrete than in bulk semiconductors. And this leads to much better usage in telecommunications and other aspects. There's also less broadening and better line widths with quantum dots because of the reasons covered earlier. For the market status, I'm going to be talking about some of the applications. So these are actually more hypothetical, as they haven't been implemented yet. So the first one is medicine. So laser surgeries rely on multiple wavelengths many times, especially eye surgeries. So having a multi-wavelength laser in one place would save space, time, and cost. In the display industry, laser projectors have actually become much more mainstream. Therefore, a laser projector with quantum dot lasers within it can actually have better color accuracy, as engineers can actually have more control over the wavelengths outputted. And in spectroscopy, the narrower line widths of quantum dot lasers can actually lead to the filters not being needed for the spectrometers, or they can make them cheaper because these filters can actually be removed. So the most well-developed application of quantum dot lasers is telecommunications. We can see Renovis, for example, a company in Ottawa, actually has a multi-wavelength laser, and it's useful because if it's low temperature fluctuation and narrow line width, and I'll explain why that is useful in telecommunications. So the cost of a quantum dot laser is actually quite hard to assign. So most of the quantum dot lasers are actually in the research and development phase right now, if not just research. But also, there's very few companies actually producing quantum dot lasers commercially, including Renovis in Ottawa and QD Laser in Japan. And their pricing is not so transparent, so anything I would say would not necessarily be true. Now, it is fair to say that the quantum dot laser is more expensive than any other diode laser that you'd see in the market, such as a quantum well laser. So this is because of the fabrication approach and also because they are not as well established yet. But we can keep in mind that there's cost savings to take into account. So if these lasers are implemented, which they already are in some cases, the cost savings is the reason why you'd want to implement them. So one of them is the cost savings from cooling reduction because of their temperature and sensitivity. So did you know that data centers actually use 5% of the total energy consumption of Canada? Well, keeping this in mind, a conventional diode laser at 85 degrees Celsius requires 3 times more current and therefore power than the same light output at 25 degrees Celsius. So a quantum dot laser, being much more insensitive to temperature fluctuations, would not require much more current from a temperature change, which means that the cooling is not to be as aggressive. So to conclude, I'll summarize what we talked about today. The quantum dot laser background and theory were explained. 2 different approaches of quantum dot lasers were explored, and the marketability of quantum dot lasers actually looks quite promising. So it's interesting to see where it'll go in the future. So here are my references, and I am showing them because this is a video, and if you want to go over them, you can see them here. And hopefully you enjoyed, and I'll be happy to take any questions.